Hi everyone, I'm Bill Hollifield and welcome to today's webinar. The topic is alarm management, particularly regarding power generation and with a special focus on the combined cycle type of operation. We know that your time is valuable, so we're going to pack a lot of information into a short amount of time. You will be able to get printouts of the webinar and so forth later on. So let's just go ahead and dive in. A little bit about myself. I've been around a long time, since about 1975. Graduated mechanical engineer and began work in the chemical industry. Did that for about 25 years. Then a nice takeover and buyout happened. Early retirement package. Of course, I didn't retire. I went to work for a great company called PAS, which is now a part of Hexagon. More about that later. PAS specializes in a variety of control system related technologies, and so I've been with them almost 20 years now. During that time, I've worked on alarm management and high performance HMI all over the world, every continent just about. And during that time, wrote a couple of books about this, showcasing the right methods for going about solving some very serious problems in our industry that span all the different sectors of the industry. It really doesn't matter. If you have a sophisticated modern control system, you probably have these problems. For almost 20 years now, I've been involved with the ISA, helping with standards, technical reports, things like that. And to my surprise, just a few years ago in 2014, they made me an ISA fellow for that. So that was quite rewarding. So we've worked with a lot of people on these technologies and helping advance the state of the art in them. Hexagon is a very large $4 billion or so manufacturing and engineering operation, and they acquired PAS just about a year ago, and it's been a great transition, and we are still around, and our technology has been incorporated into a whole variety of things that you see here. So we're going to jump right though into of which you can see that alarm management is only a small part, but that's our focus today, and we're going to jump right into it. So in the late 2000s, PAS was approached by the Electric Power Research Institute, which you may know. A lot of power companies belong to that and look to them to help them with learning about technologies that they can't develop themselves. So EPRI was in looking for good advice and documentation on how power companies, particularly generation, should do alarm management. So we worked with them to develop the first alarm management guideline issued by EPRI for power generation. After that, we worked with them to do a lot of alarm improvement projects at specific power stations. We worked with them to do webinars both in the US and other parts of the world like Australia. And then a few years later, we helped them write the alarm management guideline for the power distribution sector, which is quite different, but is not our topic today. Alarm management is about making the operator successful. It's about giving them a system that helps them understand what's going on and alerts them to abnormal conditions. When the operator is successful, all the great things that we want happen. Stable operation, good efficiency, we stay within safety and environmental boundaries, we avoid trips. All of those things require a good information system for the operator, and the alarm system is one of the most important parts of how we do that. All modern control systems do have an alarm summary screen. They in general look something like this, a list of the alarms with some sort of coding mechanisms. If your alarm summary looks like this though, is it really helpful to the operator? Is it something they can rely on, or is it just a nuisance distraction, particularly if it looks like this in an upset? This is a typical starting point, and if you have one that looks like this a lot of the time, then it's a good thing that you're looking into alarm management. There is a work process for solving the alarm problem. It's proved in hundreds of successful projects all around the world in all kinds of different industries. There have been millions of alarms dealt with and improved by this process, and it's a simple, straightforward 7-step. process. We're going to go through each of these steps and discuss them in detail, but they are specifically designed to be efficient and to give you the most bang for your buck, particularly up front in getting started and seeing results almost immediately. So we came up with a single picture that's going to show how the alarm management work process acts to improve the system. This is to show you alarms per day. These are alarms given or shown to a specific operating position, kind of one person at a time, and we're looking at the effect of the different steps on the rate of alarm generation from start to finish. Now, anytime you have more than about 300 alarms a day, it's a matter of concern. You're in an area where it is quite likely that alarms can be missed. So that's going to be kind of our starting point, and we're going to see just how much effect each of these steps has. Take a look where people normally start. Most places, when they first get involved with alarm management and they start looking at their systems, they're up at 2,000 a day, 5,000, 10,000, 20,000, in some cases even more. We've seen a lot more than that, 100,000 alarms per day. But in that case, you are going to literally have thousands of alarms every week that your operator just may not have been aware of because the alarm system is just overwhelming them. So that's what we would call unimproved. A couple of thousand alarms a day is very typical. 2 to 10 to 20,000 is very typical for power plants. I'm going to show you some data shortly. So let's start with our work process. Well, the first step of our work process is really 3 steps that we do in parallel. We can start them all at the same time. These are alarm philosophy development, analysis of your alarms to find out your problems, and something we call bad actor resolution. This is a part of the process that can go very quickly, and with a little effort, you are probably going to achieve between a 60 to 80% improvement in your alarm rate. That is quite a bit. It does not take a lot of effort to achieve that, and it really sets you up well. It may, in fact, get you down below the 300 range. It may not, but it is a fundamental, important step that you will achieve immediate results from doing. After that, we do the alarm rationalization process. This involves a little bit more time and effort on your part, but is essential. In fact, it's a required step in ISA 18.2 standard, and it will get you down generally underneath the 300 alarms per day range. You may still have an issue with your rate during upsets, but that's dealt with in the next step. Now, let's say that you then do not have some very effective management of change control on the configuration of your control system, of which the alarm system is a part. What we will see is your alarm system will drift back to higher rates and being ineffective, and that can happen within as little as a couple of years. So by incorporating some technologies that do give you effective management of change control, you can avoid that. You can stay with the improved performance that you achieve from rationalization. But you're still maybe not good on the peaks. That's when you use a technique that we're going to call dynamic alarming. It's also called state-based alarming. It's to, we'll get into exactly what that is and how it works, but with that and maybe some other advanced alarming techniques, your alarm system can be in the position of always being an excellent tool to inform your operator of abnormal conditions and help guiding them to take the correct action. So let's take a look now in detail, since we've kind of showed you where we're going. Let's take a look in detail at these first 3 steps together. Well, why start here with these 3 steps? It's because they work and they have several advantages. They really front load the benefits that you get. It does not take a lot of internal resources to accomplish them. You don't have to write big checks to external agencies to accomplish them. They're fast to do, low difficulty, and they work. They give you some really significant improvement in your performance in a short amount of time. And we, being very practical engineers, are always interested in that. So that's why we start here. So the first thing is the alarm philosophy document itself. This is not this is a highly detailed document. This is not some 4-page document from corporate saying, gee, you really ought to do alarms right, you know. So it's going to be comprehensive. It's going to be tailored to your specific work practices, the way your company is arranged, the way your tasks are allocated between the maintenance department, the engineering department, the operations department, and so forth. So it's got to be specific to address that. The more detailed you make this document, the better off you will be, because a more detailed document has you think about things up front, and you won't have to think about them later. We're talking about a 50 to 80 page document. It might have some specific appendices about your own control system, and it is a mandatory requirement of the ISA 18.2 alarm management standard. More about that later. So you don't have to reinvent the wheel on this. Hexagon, we have full instructions for you on how to develop an alarm philosophy and what should be in it. This is the table of contents of a typical well-designed, comprehensive alarm philosophy document. Basically, I show this so you will understand that every one of these is going to have a few pages of discussion about what to do and what not to do. All right, so by thinking of all of that up front, you will really save a lot of your time later when you analyze your alarm system itself and get it into a state where it is compliant with your alarm philosophy document. All right, so more detail in this is a good thing. An alarm philosophy document is a mandatory element of the 18.2 standard, and it's really the foundation on which you build your entire alarm management effort. The reason that people have problems with alarm systems is because they were initially configured without having the guidance of an alarm philosophy, where some things were thought about in advance and with the element of consistency throughout. The most important principle is that all the alarms in your alarm system need to meet this definition. They need to be designed around the operator. The operator is the customer of the alarm system. They need to indicate malfunctions, deviations, or abnormal conditions, not simply status conditions. And they need to be of things that require an operator to make some sort of response to deal with the situation that the alarm is indicating. If you did nothing else but this, you would probably have a successful alarm system. But you might think about a lot of your alarms. How many of the ones you have right now actually meet all the requirements of this definition? And very often we find that it's very few, because the alarm system is so easy to use. It's easy to just dump things in it that have no business being there. As one example of the kind of contents of your alarm philosophy document, you'll have a section on how to determine and use alarm priority, what it is, how it works, how the operator utilizes it. Your control system may have 3 priorities, it may have 24. You're going to make decisions as to which ones you use, how you use them, how they're enunciated. In general, the use of 3 or 4 is recommended, and there are some standards for the distribution of those. It's just really important that priority has a consistent meaning throughout your system. And if it doesn't, it will not be effective. There is a typical system. This looks kind of complicated, but it's really not. It's a typical system for assigning priority to an alarm. It involves a discussion where you look at what are the types of consequences that can happen if you get this particular alarm or any particular alarm and the operator takes no action or takes the wrong action. All right, what is the nature of the consequence and how severe is the consequence? And you write some words in a grid that kind of describe those things. You can look at this later. That's a grid tailored for the power industry. Okay, so now we know the kind of consequence and how severe it is. Now we look quickly at how much time does the operator have when this alarm occurs to take the right action. And the combination of those two things drops down into a grid where you decide, is this a priority 1, 2, or 3, low, medium, high, whatever the designations on your particular control systems are. It's very straightforward. It doesn't take a lot of time once you get your grids correct. And that's an upfront discussion that's going to be in your alarm philosophy. Here's another great thing to have in your alarm philosophy that will save you a lot of work. You want to look at predefining a lot of alarm design cases. You don't have to consider each and everything individually. You can think about a lot of your alarm situations and decide what is your strategy for the design of alarms like that. Okay. Typically, what about your bad PV alarms? This is alarms indicating that an instrument is not working or has gone offline or something. Bad value, bad measurement, bad quality, all those kind of things. How are you going to do those? Are you going to do those on every point, only some points, whatever? Pre-alarms, duplicate alarms, whole set of different strategies for different conditions that you can decide up front, and then you apply to all of them. Here's another example of something you should have in your alarm philosophy. You should have explicit instructions on when and when not to use a combination alarm. That is a high and a high or a low and a low on an analog signal. You never should assume that they're both going to exist. If you have a high alarm, you may not need a high. You only incorporate a high if the action the operator takes for it is significantly different in kind or degree than the action they were supposed to take for the high alarm. Only if that is true do you justify having a high or a low, same thing. Our experience is that you will eliminate about 90% of all the kind of standard combinations that people just do by rote if you follow this guidance, and it makes the system far better. You don't have operators waiting for the high to take action and that kind of thing. Step 2 is alarm analysis and benchmark. What this means is we're going to grab a lot of data from your alarm system and we're going to analyze it. We're going to analyze it in a lot of different ways. We are probably going to find that your plant will have the same problem that all the other plants in the world has, but you will have a different focus and different issues will be different on your system than the one down, in the next state. So there are a variety of metrics. These are the metrics taken from the ISA 182 standard. They are recommended. They're not mandatory, but in general, you will want to measure these things and see how you are doing compared to these target values. And if you're exceeding these target values or have some kind of issue, you want to have some kind of action plan in place to get you back in line. All right. So let's take a look at just a few of these metrics. The best one is this alarms per day. We like to look at a month's data, at least 8 weeks, whatever, and just chart how many alarms you're getting a day. And at the bottom, you've got your 150 and your 300. So on day 1 where the operator got 3,000 alarms that day, how many of them did they really look at? Could they really look at? It's not the operator's fault if he misses an alarm when you're presenting 3,000 a day or 15,000 or 30,000. So this is the first thing, and it really gives you in one glance an idea of how well off you are or how bad off you are. So here is some data. Now we did a lot of projects with the Electric Power Research Institute where we went to some of their member plants and we did improvement projects and we kept a lot of data. I'm going to show you several charts like this. This is a chart of 15 different plants. So you might say that those should be bar graphs instead of a line, but it's 15 different plants. And what we have here is the initial alarms per day from when we walked in of 15 different plants, 5 of which happen to be combined cycle. So as you can see, the first plant we were in, and they are there along the bottom with kind of concealed. We're not going to tell you exactly where they were, but 12,000, no, that was about a little over 10,000 alarms a day for a single operating position. Obviously a very bad place to be. Went into a combined cycle plant with just under 10,000. then another with about 3,000, another with maybe 2,100, and then a couple of the combined cycle plants were the best, but they were still starting out well above where you wanted to be. All right, so this is very typical to find when you first walk in the door, as that's where the alarms are, in the thousands per day. So we then like to look at alarms per 10 minutes. Take 10-minute slices and count the alarms. By definition, alarms floods begin when alarm rates exceed 10 alarms in 10 minutes and sustain themselves for variable periods of time. Now, here you see some 10-minute slices with 200, 300, 500, 1,000, 10,000 alarms in 10 minutes. In such a case, the alarm system has ceased to become useful. It's actually just a nuisance distraction. And major accidents, when you look at the alarm data leading up to them, are often in a severe flood condition. So certainly it's not helpful for anything like this to occur, and it's one of the things you analyze for. We like to look at floods. We look at how long they last, how bad they are. And then we like to look at the percentage of time that the alarm system is spending in a flood condition where it's really not useful to the operator. And so that's a useful measure. That's the one at the bottom. We have, like we often find, a system that's in flood for around 7% of the time, maybe 20% of the time, maybe 50 or more. It can get very bad. So there are examples of analyses that we do for that. So in taking that measurement, and we're looking at these power plant data, here's the very top one there. A combined cycle plant was in alarm flood 95% of the time. In other words, you have an alarm system there that is a total nuisance to the operator and is totally unhelpful to them. Not a comfortable place to be if you're the manager of such a system. And it goes down there, the combined cycle plants tend to be newer, and some of them tend to have been installed with some of the elements of alarm management kind of in their initial configuration. So they're not that bad, but still, if you had a safety system that wasn't in effect 10% of the time, you would be doing something serious about that. And your alarm system is certainly to some degree a safety system, and you don't want it to be ineffective for 10, 20, 30% of the time. The other thing we like to look at is what are our most frequent individual alarms. This will always give you some surprising data. For example, look at this chart here. Here's our top, we call these our top 10 alarms. What you will generally find is that they go off and constitute generally 25 to 80% of the total alarm load. All right, that is surprising. That means if you could make 10 alarms work the way that they should, you could drop your alarm load by 25 to 80%. There's an alarm right there on the far left that went off. I think this was about a month's worth of data. That alarm went off over 16,000 times. Now, I would say, could you design an alarm that would go off over 16,000 times? You know, maybe not, but somebody figured out how to do it, and we always see this. It probably didn't really need to go off 16,000 times in the month. So we like to look at those, identify those, because that leads right into our step 3. All of this is done by software. You do not want to assign some poor person to be doing all of these alarm analyses using spreadsheets and trying to dump data and parse it. So very sophisticated software exists out there to do all this for you. We have such software, other people do, where what we do is we automate all of this. We do it periodically. It generates reports periodically. It either emails them out or publishes them to your intranet, to internal websites and that stuff, so you can compare and see how things are going. But you really want to automate this step. So having identified those, we will immediately do step 3. We're going to find them and fix them. These are your bad actor alarms. We're going to work on maybe the top 10, 20, or 30 or so. And that does not take a lot of time to do. That is not difficult to fix these things. Here's an example. I think this was 8 weeks of data. And you had one alarm there go off 170,000 times. 6 of these top 10 alarms are individual instruments that are malfunctioning, and every time they malfunction, they generate an alarm. You know, that can be fixed. In this particular system, that only 10 alarms constituted over 95% of the entire system load. I mean, if you address these 10 alarms, you would drop the load on the operator from the alarm system by 96%. That is not difficult. There are detailed methods for doing these, for understanding these problems, and we've published those. Your expected gain, we've done this process many times. Your expected gain is going to be 60 to 80% from resolving bad actor alarms. This can be accomplished by one person part-time in just a few weeks. We are talking about chattering alarms. These are the kind that they go on, they go off, they go on, they go off, they go on, they go off. It's just chattering all the time. Fleeting alarms they come in, they only last for a few seconds and they go away. Well, obviously, a alarm that comes in and only lasts a few seconds and then goes away cannot have cleared because the operator did something. All right, so these are alarms that have some other kind of behavior problem. Stale alarms, alarms that come in and last for weeks, days, weeks, months, years. We've seen those. Duplicate alarms, alarms that are telling the operator the same thing. Misconfigured alarms, nuisance diagnostics, all kinds that we have written whole chapters in the book about how to fix these. All right, and so the information for fixing them is out there. It only takes the will to do so. So when we look at our group of 15 power plants again, we look at for just the top 10 alarms in each of these plants, how much of the load did those constitute? The one on the left, the top 10 alarms were over 80% of the total system load. In other words, you could have dropped the alarm rate by 80% on that plant from fixing 10 alarms. On the average, these were about half the load. Half the total alarm load at all these plants came from 10 unique and individual alarms at each plant. Right? And combined cycle was up there at the top, down there in the middle, and down there at the low part. But still, look at those two low ones. The top 10 alarms were almost 20% of the total load. If you did something in one day and dropped your alarm rate by 20%, I mean, people have gotten special recognition awards from doing that, and it is not difficult. All right, so we highly encourage. That's why we have this as one of the first steps. It's easy. It's easy to do. Chattering alarms are the worst kind of nuisance alarm. And we find that here's the percentage of all alarms that come from chattering alarms. And it's the same kind of thing. There are ways to fix chattering alarms. They involve using configuration parameters on the DCS like deadbands, filters, time delay adjustment, some other things. So Hexagon has detailed guidance on this step with the effective methods to do it. And we have it in a free white paper that we'll show you where to get it at the end of this webinar. So having done those things, it's very easy to accomplish a 60 to 80% improvement. So let's look now at this next step, alarm documentation and rationalization. This is another ISA mandatory requirement. It is in your future. You are going to have to rationalize your alarms. What you want to do is to do that effectively and efficiently. When you do it, you are going to, what you're really doing is you're making sure that your actual alarm system is in alignment with this new alarm philosophy that you have written. So you are going to go through basically a team effort to implement the philosophy, to come up with the changes in your alarm configuration that would reflect your philosophy. You are not going to do this one alarm at a time and actually go implement it on the system. What you're going to do is come up with a total list in a database that is what you are going to change from and to on each alarm. And then you're going to have the proper training and all that kind of stuff for the operators so they know what it means when you do the implementation. You're going to make your priority effective, your alarm settings are going to be consistent, and you're going to create a master alarm database, another ISA mandatory requirement, which is a reference and useful for a whole bunch of things, more than I can describe in this very short webinar. But it is going to be the basis for you to know if your management of change is working. and we'll show you about that in a moment. So we are going to have a team-based effort to do this. You're going to look at each of your alarms. You're going to decide, well, should this alarm exist at all? Does it indicate an abnormal condition? Does it require an operator action? If it doesn't, you're going to mark it for deletion. It should not use the alarm system. Now, that's not to say that it isn't indicating something that's important to the operator, but it doesn't necessarily qualify to do that by using an alarm. That's why you have process graphics and other ways to tell the operator what is going on. Not everything needs to be an alarm. An alarm is an intentional interruption to the operator. It's saying, look at me, I'm important. Well, the fact that something you've automatically programmed to go from step 1 to step 2 has operated successfully doesn't mean you should have an alarm to say, thing A has gone to step 2. You might need an alarm that says thing A was supposed to go to step 2 and it hasn't. That's a different thing. So you're going to look at process history to determine your set points. You're going to look at a lot of things. This is a team effort, and it can take a while, but there are ways to do it efficiently as well, and we've written like a whole chapter about that. An example of this is you're going to determine where your alarm set points need to be. Now, you may have equipment. It may be from the manufacturer about your equipment that says where they need to be, and so that could be the answer. And sometimes that is the answer, and they're not there, and you need to change them. But you're also going to look at where does your process like to live, and you don't want to set your alarm right in the middle of that normal operating zone. And you would think, well, nobody does that. Well, believe me, everybody does that. You're going to find a lot of your alarms when you look at your data that are just right in the middle of your normal process variation, and that's not what you want to have. Your output of this is a master alarm database. The right database tools in doing this and documenting alarm causes and consequences and corrective actions and set points and all of this stuff, the right database tools will save you time and money. If you try to do this using Excel, something like that, you're just going to waste a lot of your own time and money, and you won't have a product in the form of a master alarm database that is very useful for you going forward. And believe me, there are a bunch of great uses you can make of that information. One of those uses is, in fact, to expose it to your operators. And we're not talking about in some 2,000-page book that sits in a closet. We want to integrate this in. For example, if the operator is looking at a graphic and there's an alarm on that, it would be nice if they could simply select that arm, and a faceplate could be called up that retrieves data from your master alarm database that shows them, well, what are the common causes of this alarm? What are the consequences? What do I need to do about it? Maybe even link to a procedure. Okay, this is a very common thing that people are doing, and it's one of those things that helps make your newer operators as effective as your more experienced operators. Okay, they can see what this team of experts had to say about every alarm with just a click. So this is a highly useful thing to do. To do that, you need a database. The results of alarm rationalization are consistently reported by the people that do it in a positive way. The alarm system makes sense. It's useful now. It sure wasn't before. All these kind of quotes. And the other thing that you see is that the benefit of doing alarm rationalization goes beyond the alarm system. The quote there you see from a chemical company ops supervisor is quite typical. It gave them insight. It showed them mistakes in their P&IDs. In general, there were misunderstandings between engineering and operation as to how the plan actually worked, and the alarm rationalization exercise helped reveal that. So everybody's happy once you're finished with alarm rationalization. You're glad you did it. Some people like to avoid it. It does take some time and effort, but there are ways to do it efficiently that we wrote about. So what good does it do in terms of these 15 plants? Well, what we look at is what is the percentage reduction in configured alarms? That is, how many configured alarms did I have before and after the rationalization effort? And generally, it's quite significant, 16 to 92% reduction, meaning that a lot of the alarms that were configured in the system were totally unnecessary, did not meet the definition of an alarm, or were duplicates of things that did meet the definition of an alarm. So here you can see the combined cycle plants. We had 4 examples of that, of 75, 62, 26, 16% reduction in the configured alarms. All right. The result of rationalization is, as you see, you take an alarm system that is 1,000 alarms per day, 2,000, 3,000, high peaks of 10 to 15,000, and you get it down most of the time into the desirable range of less than 300, with maybe some slightly higher rates during upsets. This is exactly what we're looking for. So that's where we are. So what is the next step? We want to look at alarm, audit, and enforcement. Because what we have typically found is that there's often poor management of change control of the alarm system, and that alarms rates will creep back up. Alarms will continue to disappear, to be reintroduced to the system without following the new rules. So control systems are notoriously easy to change. A lot of people have access to them. The security is poor. It's not very granular. I mean, if you hired me to come in as a contractor and work on your alarms or work on almost anything, I would probably have access to change a whole bunch of things that you wouldn't want me to change. Okay, so we kind of need to deal with that. Your alarm philosophy represents a bunch of new rules as to who is allowed to change things in the system, and a lot of people don't get that message initially. They've been changing the alarms to suit themselves for years, and that's no longer desired. So what we typically see is that there is an entropy. If you don't do something, your alarm system, after your rationalization, it will drift unless you have very good management of change control. You'll have lots of unauthorized changes, so we want to watch for those. So there's an automated way to do this. You've got this master alarm database that you produced in DNR, okay, documentation and rationalization. Well, you put that on a server. The server has a connection to your control system, and it periodically reads the control system configuration and compares what it finds to the master alarm database. Any changes are unauthorized because a proper change to an alarm following your MOC procedure should have also changed the master alarm database. So if there's any change at all, it's from somebody that did not get the message and did not follow the rules in terms of alarm system management of change. Now, you may have a few alarms that are so important to you that it's not enough to just generate a weekly report and have somebody follow up on that and try to figure out, who's changing the alarm system that's not supposed to. You may have some that are so important that you say, well, I don't care who's doing it. If we find such an example, we're gonna write it back in its correct configuration right away. That's called the enforcement part. Now, you can choose to do that on some alarms, a very few alarms, once a day, once a week. A lot of people run the audit and enforce function, every shift, every day, every other day, something like that, and operate on a small subset of alarms that they enforce. So with that technology, what happens is your alarm system will stay for years in the configuration state that it should be, but you still may have those peaks. So let's talk briefly about dynamic alarming. Also called state-based alarming. It's one of 3 or 4 different techniques that I won't cover all of them, but what we're talking about here is automatically altering alarm set points, priorities, and suppression status based on the current process state. And here's a very simple example. Let's say we have a compressor that's running, all right? It's running, everything's fine, you have no alarms. That's exactly what you want. Well, let's say that something shuts down that compressor. It could be a lightning strike. It could be a variety of things, but something has caused that compressor to shut down. It could be an automated shutdown system on low oil pressure or something. But when that compressor shuts down, you may immediately get a flood of things that you totally expect to happen? Obviously, you're going to get low flow. You're going to get a low discharge pressure and a high suction pressure. Well, those are all irrelevant to the operator. If the operator knows the compressor is shut down, those are all expected. So we don't need this alarm flood. What we want to do is to dynamically suppress the alarms that are what you expect when the compressor shuts down. We still alarm the fact that it's shut down, but we don't let all those alarms obscure the important alarms from the rest of your process as it adjusts to not having a compressor there. All right, and that the operator really is the one, those are the ones the operator really needs to address. So we can dynamically suppress those, and then when the operator is ready to restart the compressor, you can unsuppress those, bring them back in, and not have to deal with a flood of alarms that obscure their view of the other parts of the system that whose alarms are more important in the immediate aftermath of the compressor shutdown. So that's an example of state-based alarming. So now we are where we want to be. The object is just you do control and maintain. We do that by continuous monitoring of all of those measurements that we take in the alarm system, the alarms per day, the flood measurements, the alarms for 10 minutes, we monitor for uncontrolled suppression, we monitor for unauthorized change, a lot of stuff. And then when anything those metrics tell us, we deal with. We do bad actor resolution, we do audit and enforce, we fix chattering alarms that occur. All right, so that's kind of our the seventh step is to maintain that. There's a standard. ISA 18.2 came out in 2009. It gets updated about every 5 years. It'll probably be updated in about another year. It is applicable to power generation, okay, and it does have regulatory impact. Regulatory agencies like OSHA will enforce ISA and ASME standards, all right? Even though they are not regulations, they are considered recognized and generally accepted good engineering practice, and you can be fined and penalized by a regulatory agency for failing to do what a standard says you are supposed to do. So the standard has mandatory contents, recommended contents. It only contains the what, not the how. Doesn't tell you how to solve these problems or give you any examples. It just says you have to do these certain things. We have a detailed white paper on understanding and applying ISA 18.2, or if you're international, there's an international version called IEC 62682. We have a detailed white paper to help you understand what a standard means when it says a certain thing, and particularly what 18.2 means. Now, this is all well and good. Your alarm system is great. It's alarming only things that are important. But here's a question for you. If you call up your graphics, can your operators find the alarms? Okay. If your graphics look like this, they can actually interfere with your operator's ability to deal with alarms, to recognize them, to attain and maintain situation awareness and do their job. That's, however, another topic we won't be discussing today. It's called high performance HMI, and we have white papers on that as well. It's a very interesting topic. But if your graphics look like any of these examples here, you really should read the white papers. Okay, one of them actually has power generation examples of kind of before and after, so you might find that interesting. In summary, poorly performing alarm systems are contributing factors to major accidents. This has been proven. These correlations have been shown. Many accidents have been analyzed and found this to be true. Alarm management is a very mature set of knowledge and principles. They are well known. They are easy to apply. They should be applied consistently. This problem has been solved at many places. So if you're just getting started with alarm management, you don't have to go off and experiment. The ways to fix your alarm systems are fully known. So don't reinvent the wheel. Apply what's known and what you know that works. You have a page here. You can get the download page here of several resources to help you. And we love at PAS and Hexagon to do white papers that are actually usable and useful. We don't do, these are not papers that are describing products. These are papers that describe principles and methods and things that if you take your valuable time to read a paper, we want you to be able to do something with it right away. Okay, so that's our goal in writing these. So we have them on all kinds of things, particularly nuisance alarms you might be interested in, understanding the standards, the technical reports that come with the standards, HMI, that kind of thing. And the books are available and so forth. And we also have products and services. We have software that does everything you've seen and a whole lot more, and that can actually take you beyond alarm management into such things as boundary management, know exactly when your plant is having an excursion from any of your predetermined boundaries. So it's very neat stuff that you can check out. So at this time, we will go into the live mode. I hope you have some questions. You can also email me with questions here at my address, bill.hollifield@hexagon.com. And so we'll now end this part of it and go on to the live portion. So thank you all for being here.
Thank you, Bill. Now we're in the discussion and Q&A section. We've seen some questions come in via chat that Bill has been preparing answers for. I guess, Bill, would you like to take it away? Bill, are you there?
Scott, I'll hi everybody. This is my name is Brian Nixon. Scott, can you hear me okay?
Yes, I can.
Okay. I'll since Bill temporarily unavailable, technical difficulties, I'm sure. I'll go ahead and take a stab at some of the questions. So I guess I could start with some of the things that have come in the chat, and then go back to some of the questions that were submitted previously. So the first question from Peter. Are there any outage or other data available that can help justify the expenditure for alarm management? So this is something that it's very difficult to have a direct causation between, doing really good alarm management and seeing improved cost performance or economic performance. The ASM, I believe, the Normal Situation Management Consortium has some numbers that they say, about $2 billion, somewhere between $2 and $4 billion is lost in general industry every year due to abnormal situations that could have potentially been avoided, right? They estimate that's anywhere between, $100,000 to $1 million at a given plant. And the whole idea is that these abnormal situations could be better managed so that you avoid those plant trips, load losses, etc. So while there's not necessarily a direct line between do alarm management, get this much money back, right, as a return on investment, what we do see at a lot of our customers across all industries and just industry in general, when you are really good at alarm management and high performance HMI, you just have better results. You don't have as much variation in the process. You don't have as many disturbances. Your pager doesn't go off quite as often when a unit has to run back or anything like that. So while there's not necessarily a direct line, there are some ways to kind of estimate it based off of any incidents that you might have had at the plant site, where we can identify, well, an operator could have avoided this if they had better information up front, but not necessarily a direct line. So it's very, very difficult to do. Hopefully that gives you a little bit more information about the question. Okay, so the next one from Christoph. Being active in aviation too, I wonder how old-fashioned alarm management in power plants is compared to modern aviation. Keyword ECAM and electronic systems showing you the relevant alarms for an abnormal situation only, inhibiting lower level alarms and giving guidance on how to solve the issue. I understand this is somehow implemented in master alarm databases, but my impression is that they are still not common. When in power gen, when power gen will be on the same level as aviation is today. Unfortunately, Bill is the aviation buff. I am not quite as active at all, really, in aviation. I've been on a couple of flights here and there, but nothing quite like Bill. What I will say, though, the concept of state-based or dynamic alarming, it's been an industry for years and years and years. But just like alarm management has been around for years and years and years, we see that it hasn't really been adopted everywhere. It's not quite as widespread as as some other philosophies or some other things might be. So I know that automation system vendors are always looking at are always looking at ways to improve their own products and to kind of bake in some of these concepts so that they can be available for end users to really
test.
There you go. Hey, there's Bill.
Okay. Doing a great job. Thanks, Brian. Can you see this screen? It says webinar questions. Is my screen sharing?
Yep.
Okay. So, yeah, let me bail you out here.
Thank you.
Let's see. So a bunch of questions came in before the webinar. So I've tried to put a few things together, then I'll address the others, but Brian's already addressed some of them. So I had a question: what is the best practice for alarm prioritization? What should be defined as priority one? The answer is here. In the alarm philosophy document, I zoomed in on that grid. If you have an alarm by which the console operator's action is the means by which harm is avoided to some person, then that alarm, it really bypasses the whole thing. That is definitely going to be one of your priority one alarms. We'll just call them priority one, critical, whatever, your highest priority alarms. That's not exclusively the use of that priority, but that will. Now, what you have to then do is, well, what are circumstances in which the console operator getting an alarm is the means by which something harm to a human is avoided? And there are some just very specific cases here. We list those in the philosophy section of the book. Flammable and toxic gas detector alarms, those should be shown on some kind of geographic screen as to which alarm it is, and the board operator should know where people are working. If maintenance is working on something and they get on the intercom system and they say, get out of there, head south, whatever. That's one such example. Smoke or fire alarms, automatic, the activation of safety showers or eye baths or deluge systems. Obviously, you want to send help to those areas. If somebody is using a safety shower, that means they've been exposed to something. You need to send help to those people. Presence of hydrocarbons, several of things such as those are examples. And if you come up with other examples, I mean, in a coal-fired plant, for example, you've got coal conveyors, and there's generally some sort of automatic safety rope attached to those. And if you get your clothes hung up in one, man, you want to pull that rope to stop the conveyor, and that should also cause an alarm for the board operator to send some help to that area. So those are the kind of things, and for critical process stuff, that's another thing. So let's see, priority one, pre-trip alarms, just so you know, you have a lot of alarms that say, take low oil pressure. A low oil pressure alarm is saying, if you don't do something about this oil pressure, I'm going to get to a point where probably the automatic trip is going to operate. So that pre-trip alarm, while the operator still has time to address the situation, is probably going to be a higher priority than the actual alarm when the compressor or when the device trips. I mean, if you can successfully address the pre-trip alarm, you can avoid the trip altogether. So those are much more significant consequences. Now, you still need an alarm that something has tripped. It might or might not be the same priority, but the only thing the operator can do at that point is to figure out what caused the trip and to get it running again. You cannot avoid all those other consequences of a trip. We had a question on what are the latest alarm statistic performance values. The guidance in ISA 18.2 is still essentially the same. I've printed it for you here. By the way, we have white papers on understanding and applying 18.2. We have separate white papers on almost every one of these steps that we talked. Really good one on solving your nuisance alarm problems and that kind of stuff. So these are the ones, 150 to 300 a day, that kind of thing is all still the same. There's things like you want to be looking for unauthorized alarm suppression or improper alarm attribute change. That means someone suppressed an alarm without doing it in the right way. Somebody changed an alarm priority or changed an alarm set point without changing the master alarm database. Okay, if somebody changes an alarm set point once you've done alarm rationalization, that's basically just not allowed, and it shouldn't be done except via a management of change process that would have updated the master alarm database. So if you ever find a discrepancy between what's actually on your system and what's in the master alarm database, that's a problem. Somebody's not following your rules. Now, you may have a very few alarms that you want to be, analog alarms that you want to be operator adjustable. Fine. You define the ranges that are appropriate and you provide a separate screen that shows all those so that at shift change, everybody walking in can understand where these operator adjustable alarms are currently set and even why they are set where they are. So you just in the aviation example, and I love aviation example, I currently have 1.5 airplanes, but you can't imagine how bad it would be. The airplane, the airliner arrives, the pilots get out, the next 2 pilots come on board, and they have no idea where all the alarms are set for that particular airplane. No, that's just not allowed. That would be crazy. So it's not allowed in aviation, and it shouldn't. Shift change shouldn't be a lot of guesswork as to where did the last person leave all these important alarm settings. You don't want that. There was one question about how do I arrange my alarm summary screen so that really what you're looking at here is an example of a best practice. You've got your alarms separated. These are your current alarms separated in priority bands, and within each band you've got the most recent one on top. So there's a couple of priority 1s, 2s, a few priority 3s, a few priority 4s. So the question is, well, how do I do that? I'm sorry to tell you that the answer, and you're not going to like it, is read your manual. All right, it's going to be a different thing for every control system out there, but all alarm summary screens from modern control systems now are generally configurable. And those options are buried in very boring chapters and sections of that voluminous user manual stuff that you got. So the only answer to that question is pull out your documentation, read the owner's manuals, call your technical support for that particular control system, and you can. I don't know of any alarm systems that you can't make work like this, and this is kind of seen as a best practice. Let's see. How do I do this? How do I do alarm management with very limited resources and manpower? Well, start by doing the first 3 steps. That's why we put them there, and they don't take a lot of either internal or external manpower. And when you get to step 4, read all of the stuff that we have about, for example, rationalization. We put in an entire chapter in the Alarm Management Handbook based on experiences to how to do that well, how to do it right, and how to do it in a cost-effective way and not backtrack and redo things. So we advise actually that you get experienced help, people that have done rationalization, have them help you work through that process. You're going to find that it's money well spent. We always say that if you hire us to help you rationalize your alarms and you don't think we're actually saving you way more than what you're paying us to do that, well, fine, cancel the contract. We've never had anybody take us up on that because it's recognized that if you get good help with it from people that know how to do it, you can do it faster than cheaper than if you just try to figure it out yourself. We had a couple of comments really about state-based alarming. How do you do that? Well, this is a very short webinar. This is trying to tell you an overview of the entire process. We have separate webinars about doing state-based alarming and how that works, how to make it work. Now, if you were to try to do this using the onboard capabilities of your alarm system in terms of configuring internal logic points and all that kind of stuff, well, good luck. Frankly, it's almost impossible to keep that stuff up to date, to make it work well, you know, like if you're inside a Honeywell system or a Emerson or something trying to do that. That's why PAS created more than a dozen years ago a product. We don't talk a lot about our products, but we have a kind of a bolt-on system that does all of this stuff, including dynamic alarm management, boundary management, a whole bunch of other things, and including state-based alarming, where you pre-configure what are your states, and then you have the logic that detects the states, and then our automatic system continuously evaluates that logic and adjusts the alarms to match your process state. But that's not something we can talk about in 5 minutes, you know, and certainly not as part of an overview webinar like this. There were a couple of questions that I didn't understand. There was one about effective use of conditional alarms. I don't know what's meant by conditional alarms. Relevant alarms that required a lot of analysis. I'm not sure what that is. And then some plants have 2 separate alarm systems, one for the balance of the plant, one for the turbine control system. Are these really 2 separate DCSs? Are the alarms truly different? Are the systems truly different? There's a common thing in the process industries where you have like a skid system that does something like refrigeration, and you bring in those values into your main control system so the operator really has one place to look at them instead of having some auxiliary panel that the board operator has to monitor that's just the stuff from the skid system presented in a different way and maybe inconsistent with the rest of it. So I would say there's my email address. Okay, bill.hollifield at Hexagon. Send me any questions you have. Okay, I love to get questions through the email that lets us go into more detail about specifically what you're talking about. And I can probably, in many cases, provide some supplemental materials that aren't on the websites. I mean, we're migrating our websites and have been for a while. So I can provide you with stuff that's not on there that might help address your situation, and plus we can have discussions. Scott, did you let's see, I think the ones that I think we've answered the ones that kind of came in late.
Yeah, one just came in from Robert Threlkeld. His 2 combined cycle plants had 2 alarm systems, one for the DCS and one for the GE Mark 6E.
Mm-hmm.
So I think that was clarifying the question of the 2 separate alarm systems.
Yeah, I think we see that a lot in the power industry where the turbine controls have their own separate HMI, own separate alarm screen, and then the balance of plant, as they call it, automation system has its own alarm summary screen and HMI, et cetera. And our typical advice, and Bill, you can back me up or correct me. Our typical advice is try to have a single consistent interface that the operator will interact with. A little bit different industry, but I was once offshore and they had a similar condition with their stuff below the water and the stuff above the water kind of thing. And I remember doing an interview with an operator, and they had a bit of an alarm management problem. The operator at one point would actually kind of swipe behind him trying to turn the horn off, and so he's just kind of randomly swiping, smacking at the keyboards to try to get the alarm from one system. He didn't even turn around to figure it out. That was causing problems. And so the idea is, when you hear the alarm buzzers and things go off, you don't want the first reaction the operator to have be, okay, which system is it coming from? So I think we generally advocate for a single consistent interface to display alarms to the operator, and hopefully that same interface is the one where they would actually respond to the alarm as well using the HMI.
Anything else
Yeah.
I missed?
I'm pretty sure we covered all the bases here from the chat. If
I'm
anybody
reasonably
else,
certain I did not do Christoph justice around the aviation question, being active in aviation. When will power gen basically reach the level of aviation? I'm certain that I didn't do it justice just because I'm not as familiar with aviation. Bill, would you mind maybe take a look at that one?
Yes, I've got that here. I would say that we can learn things from the aviation industry, but it's very different. I have Dynon Skyview in my aircraft, which is a wonderful electronic flight information system, and there are things that are done in aviation that are really good. And when you start talking about high performance HMI, there are some lessons that we can learn from that. But aviation has its own history and its own kind of prejudice, and there's some over reliance on color and things like that. So we look at it and we can learn from it, but it's not that we would just adopt it. In terms of this question, I think we can learn more about it from HMI than in alarms. A lot of the alarms, well, I'm not going to go into that. Every flight, all the engine data is recorded and it's gone over by experts that and doesn't concern the pilot. So I think the answer to the question has to do more with the proper application of state-based alarming, so that alarms are relevant to what the process is doing. That's similar for the question where people were wondering, well, I have a section of my plant that's shut down most of the time, and so I get alarms from it. Well, I'll give you a quick example. Imagine you're going to have a tank that's going to be shut down and it's supposed to be empty. Would you just suppress, and this is going to be for 6 months, it's supposed to be depressurized and empty. So for that 6 months, would you just suppress the alarms from it? I would say no. And we have an example we've written about here. If the tank is going to be empty, you should still have a high level alarm on it, but you would probably set that high level alarm at something like 2% to detect any inadvertent or improper introduction of material into a tank that's supposed to be empty. Now, when the tank's in operation, the high level alarm might be up at 80%. But when it's not in operation and it's supposed to be not in operation, you might have that dynamically set to 2%. Same for pressure. Normal operating pressure when it's running might be, 200 pounds, I don't know. But when it's supposed to be emptied and depressurized, you might have a high pressure alarm set at 10 pounds. So these would be examples of using dynamic or state-based alarming to still have proper and useful alarms on equipment that is not being currently operated. It's just that those set points and characteristics would be different. Here's one thing for you. We never, ever, ever alarm something just because it is off. And people say, what? No, we never alarm something just because it is turned off, because it's often that you turn something off intentionally. That should not cause an alarm. We alarm something that is off if it is supposed to be on. That requires some logic, that requires some thought, but we never just blindly alarm things whenever they're off, because you'll fill up your alarm summary screen with things that are not alarms and should not be there. Remember, contact me, email me, and we can discuss all of these questions offline and in more detail. And a lot of people also don't like to ask questions in kind of an open forum, and I understand that too, and that's why I love to get questions via email.
thanks so much, Bill. I believe the slides are going to be available to all the registrants today.
We intended we intend to PDF this presentation and make that available to you.
That's great. And then we also have the recording available and all the links to the white papers and webinars that Hexagon has published on their website. So that's be easily accessible for everyone to get more information.
Right. That's not all of our white papers. Like I say, we're undergoing kind of published material migration. So I probably have a lot more on a specific topic than has currently been changed and published via the Hexagon website. So it's a part of the transition. But anything I have is you can contact me on it. It's great. It's best if you can go through the website and find it there, because if you follow these links that we give you to the website, you'll probably see other papers that you're interested in. But if it's something specific and you can't find it, let me know.
Great. Well, thanks so much for an extremely informative presentation today. And thanks everyone for joining in and spending part of your day with us. Have a great day.